So today we're going to talk about Lesson 2, graphing general rational functions. In Lesson 1, we talked about how to graph simple rational functions. So today we're going to look at rational functions of higher degree polynomials. So to start us off, I have a table in front of us that's kind of going to give us a better idea of what some of these characteristics are, what polynomials of higher degree look like, and there's going to be a handful of properties that are going to go through that are going to pertain to these graphs. So to start us off, rational functions of higher degree polynomials are going to have a little bit of a different look to them. There's still going to be function, we're going to call this your f of x. So you have your first, we're going to lead off with function f of x. But you're going to have a polynomial on top divided by a polynomial on bottom. Or other words, you're going to have an expression on top divided by an expression on bottom. And the difference here is we're going to have higher degree, which means we're going to be looking at polynomials with more than necessarily just your x or x squared. We're going to be looking at higher degree numbers there. So if you have a rational function that's in this form, it's going to have the following characteristics. So the first is your x-intercepts. So as we go through and we start graphing, your x-intercepts, which we remember as when we're graphing, it's where your graph crosses your x-axes. Your x-intercepts can be found if your numerator, by finding your numerator's real zeros. Or in other words, we're taking our numerator, which in this case will be p of x, and we're going to set it equal to 0 and find its real values, real zeros. By doing that, that's going to tell us what our x-intercepts of our rational graph will be, rational function. Our second bullet point is f of x has a vertical asymptote at each real zero of q of x, which is your denominator. So to find your vertical asymptote of these more general rational functions, we are going to set your denominator equal to 0, find those real zeros, and that's going to be where your vertical asymptote is going to be. And f of x has at most only one horizontal asymptote when we have the following characteristics. So we have to analyze in each given example or equation that we're going to be given, we have to actually analyze where our horizontal asymptote is going to be. So if you look back up at the top, our leading, or our degree, which is our leading exponent, that's going to be called m. Our leading degree or exponent that is going to be in our denominator is going to be called n. So if our numerator numerator degree is less than our denominator degree, then the line y equals 0 is going to be our horizontal asymptote, which is essentially our x-axis. If both of our degrees in our numerator and denominator are equal, then the line y equals a over b, which will just be the leading coefficients of our numerator and denominator. That line will be our horizontal asymptote. And if your numerator degree is greater than your denominator degree, then we're going to have no horizontal asymptote. So let's look at an example. Off to the right, I gave you an example to see if we can put this into use with these characteristics. So here we have function of x. So this is our graph, our rational equation that we want to graph, is equal to x over x squared plus 1. Okay, so the first thing we want to do is we want to find our x-intercepts. And we know from The left side of our table, that our x-intercepts are found by basically setting our numerator equal to 0 and finding our real zeros. So if we look at our numerator, we're going to set our numerator equal to 0. And when we do that, because our numerator is just x, we get x is equal to 0. So we know we have one x-intercept for this graph, and it's going to be x is equal to 0. Our vertical asymptote has us setting our denominator equal to 0. And if we do that, we get x squared plus 1 is equal to 0. If I subtract both sides by 1, I get x squared is equal to negative 1. And we know if we square root both sides, we're going to get an imaginary number here. So we get x is equal to plus or minus the square root of negative 1, which we all know is actually x is equal to plus or minus our imaginary unit. And since we have our imaginary numbers here, we have no real solution. So since we have no real solution, we also have no vertical asymptote. I'm going to write that up here. No vertical asymptote because we have no real solution when we set our denominator equal to 0. So we have no vertical asymptote for this example. Our horizontal asymptote we find by taking the degrees of our numerators and our degree of our denominator and analyzing them. So in our numerator, x, if it has no degree listed, we know that there's an invisible 1 that's up there. So we take our degree of our numerator, we take our degree of our denominator, which is 2. And since 1 is obviously less than 2, we're going to be comparing them. Therefore, if I look over on my left-hand side, since 1 is less than 2, I'm obviously going to go with my first characteristic, right? My first horizontal asymptote, which is y equals 0 for your horizontal asymptote. So in this example, we just wanted to find the x-intercepts, the vertical asymptote, and horizontal asymptote. We're not actually going to graph this particular example, but that's how you would start setting up your graph for these rational functions. So let's go ahead and look at example 1. So in example 1, they give us a new rational function, and they want us to graph the function, then state the domain and range. Okay, so the first thing we're going to do is we're going to start off by finding our x-intercepts. And again, x-intercepts is found by setting our numerator equal to 0 and then solving. So if we set our numerator equal to 0, since it's 4, there is no variable, therefore we have no x-intercepts. So since our numerator has no variable, we can't set it equal to 0, we have no x-intercepts that's going to be part of this graph. So let's look at our vertical asymptote. We find our vertical asymptote by setting our denominator equal to 0. So if we find our denominator, x squared plus 1, x squared plus 1 is equal to 0. This is going to look just like the previous example we just did together. I'm going to subtract 1 from both sides, and we know that this is going to give us an imaginary unit again. So because we have no real solution, we also have no vertical asymptote. Lastly, we're going to look at our horizontal asymptotes, and we find this by setting our degree of our numerator, our degree of our denominator, and analyzing those. So first we start off always with the degree of your numerator, which in this case, because we have no variable, our degree is going to be 0. Our degree of our denominator is obviously 2. Since 2 is less than, or 0 is less than 2, we know that the y equals 0, or our x-axis, is going to be our vertical asymptote. So if I just go ahead at this point, just because I'm going to highlight, and you guys can grab a highlighter too, or you can just use your pencil and draw a strong dashed line along your asymptotes. But we have no vertical asymptote, so we can't draw a vertical asymptote, but we can draw our horizontal asymptote. At this point, off to the right-hand side, I've given you a graph, and that graph, or a table with x and y. So at this point, what we're going to do is, because we have no vertical asymptote, I'm going to graph some points a little bit to the left and a little bit to the right, including 0, just to get an idea of where our plotted points are going to be, our ordered pairs. So I'm going to actually graph the points -3 for x, -2, -1, 0, 1, and 2. And what I'm going to do is each time I'm going to set these numbers in my equation with my calculator. And I'll show one for you to start us out. So to start us off, we're going to have 4 divided by the quantity. And I'm going to put 2 parentheses here because I'm going to have x squared. So this first parentheses counts for our entire denominator. The second parentheses is going to help us plug in this number in for x squared. So since I'm starting with -3, I'm going to square -3. Then I'm going to add 1 and then end parentheses and hit enter. And I get 0.4. So at -3, I get 0.4 for my y value. So I'm going to continue doing that with -2 all the way up to +2, and I'm going to get those values. So if I do that all the way through, if I plug in -2, I should get 0.8. If I plug in -1, I should get 2. If I plug in 0, I should get 4. If I plug in 1, I'm going to get 2 out. And if I plug in 2, I'm going to get 0.8. And again, you can find those points by doing exactly what I did with your calculator. From there, I'm just going to plot these points. So 0, 1, 2, 3, 4. +1, I'm at 2. +2, I'm at 0.8, which is just below 1. If I go to the left, -1 is at a +2. -2 is at a 0.8. So if I go -3, 0.4. And what you'll notice here is because you have your horizontal asymptote, you know that your graph cannot cross that horizontal asymptote. You're going to end up with a graph where you get closer and closer to that horizontal asymptote, but you're not going to cross it. And the arrow should be pointing down, so it's getting closer and closer to both ends of those graphs. And that is your graph that represents example 1. At this point, if I look at my domain from my graph, my domain, again, remember, deals with your x's or your inputs. Your range deals with your y's or your outputs. Your domain, so if you look at your x's, which is along your x-axis, your graph spans -x, includes 0, and spans positive x values. So you know that your domain is going to be all reals. And your range, again, deals with your y, so you're going to look up and down on your y-axis. From here, you know that your graph is in the positive y's. You know you have no negatives. And you actually get closer and closer and closer to that y equals 0, but you're never going to actually touch it. Because if you touch that y equals 0 line, you would be touching your horizontal asymptote. And you know that your horizontal asymptote's there because your graph cannot cross it. So therefore, your maximum y value here is 4. Your lowest y value is going to be really close to 0, but not include 0. So your range is going to be between 0 and 4. And make sure you include 4. Moving on to example 2, let's check out a couple more examples here. In example 2, we have the graph y equals 3x squared divided by x squared minus 4. So the first thing we're going to do is we're going to find our x-intercepts. So again, we're going to start off with taking our numerator, setting your numerator equal to 0. Divide both sides by 3. We get x squared is equal to 0. Therefore, you know your x-intercept is going to be at 0 with a double root. Put that double root down. Your vertical asymptote is found by taking your denominator and setting that equal to 0. So x squared minus 4 is equal to 0. Add 4 to both sides, we get x squared is equal to 4. Square root both sides, since it's a positive 4, we can get x is equal to positive and negative 2. You could also, right off the bat, if you wanted to, if you didn't set it up the way I did, you could have FOILed, or factored, I should say, and you could have gotten the two groups x minus 2, x plus 2, and that would still give you the same x values back out. Your horizontal asymptote, again, is by setting up your degrees of your numerator and denominator. So you take your degree of your numerator, which is 2, the degree of your denominator, which is also 2, and because these two are equal, if you refer back to that sheet from the first page, because they're equal, the line y is equal to a over b is going to be our horizontal asymptote. So if we set this up right, we know that our y equals a over b line. Well, your a is obviously the 3 in front of your x squared. In this case, that invisible 1 is in front of your x squared. So you take your leading coefficients of both your numerator and denominator, and you can circle out those numbers. So your y equals a over b is going to be 3 over 1. So you know that y equals 3 is going to be your horizontal asymptote. So at this point, before I move on, I just want to set up my vertical asymptotes with a light sketch or highlight of my horizontal and vertical asymptotes. So here, I'm going to go negative 2 is one of my vertical asymptotes. Positive 2 is going to be the other vertical asymptote. And you have to be careful about your horizontal asymptotes here, because there are going to be some examples that we'll deal with where your horizontal asymptote, depending on how your vertical asymptotes cut your graph up, they may be a little bit different. But for this case, we're going to, 1, 2, 3, I'm just going to write a light highlight across my horizontal asymptote. So at this point, I'm just going to, again, start off where I'm going to pick x values to plug into my table here to get some y values out, so I get some ordered pairs to plot on this graph. So because of how my graph is divvied up with my vertical and horizontal asymptotes, I want to make sure that I pick values for x that are going to be less than negative 2, between negative 2 and positive 2, and obviously greater than 2. I'm not going to pick 2 and negative 2 at all for my x values, because I know that my graph cannot hit x at those particular values. So I know I'm going to jump around a little bit. So in this case, I'm going to start off with negative 4, negative 3, so a few points to the left. Negative 2 is not going to be included, but I'll jump to negative 1, 0, and 1, so I'm going to include the middle points in here. 2 is obviously not going to be included, but I'll pick 3 and 4 and extend my table a little bit to get some y values here. So how I'm going to use my calculator for this, I'm going to start off with negative 4. So if I plug this in my numerator, I'm going to plug my numerator in parentheses. So 3 times, and I'm plugging in negative 4 here, my first point, negative 4 squared, that's my numerator, divided by, I'm going to do 2 parentheses again. The first parentheses to cover my entire denominator, and then this inner parentheses for that x squared at the beginning of my denominator. So I'm plugging in negative 4 squared minus 4 end parentheses, hit enter, and I get 4 back out. Let me see, which should not be negative 4 squared minus 4.